Okay, the third objective of section 1.5, the limit of a function, we have the oxymoronic topic of infinite limits. Let f be a function defined on both sides of a, except possibly at a. So in a open interval about a number a, next value, then the limit as x approaches a of f of x equals infinity, means that the values of f of x can be made arbitrarily large, that is, as large as we please, by making x sufficiently close to a but not equal to a. Again, we don't care about equaling a, we just care about what happens when we approach a. Another notation is f of x approaches infinity as x approaches a. Again, the symbol is not a number. Infinity is not a number. But the expression, the limit as x approaches a of f of x equals infinity, is often read as the limit of f of x as x approaches a is infinity. Or f of x becomes infinite as x approaches a. F of x increases without bound as x approaches a. This definition is illustrated graphically in this figure. So x is getting close to a, we're approaching a. In the meantime, f of x is getting higher and higher and higher, just exploding as we approach a from either the left or the right. And so the y values are increasing without bound. We can make them as high as we like. Name any number you like. The largest number you've ever heard of, we can make it larger by letting x get really, 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 really close to a. A similar sort of limit for functions that become big and negative as x gets close to a is defined in definition 5 and is illustrated in figure 13. So now as x approaches a from either side, the values of x get big and negative, bigger and negative, bigger and negative, bigger and negative. Okay, so here's that definition 5. Let f be defined on both sides of a except possibly at a itself, in some open interval about the x value a. Then the limit as x approaches a of f of x equals negative infinity, means that the values of f of x can be made arbitrarily big negative by taking x sufficiently close to a but not equal to a. The symbol, all of that symbol can be read as the limit of f of x as x approaches a is negative infinity, or f of x decreases without bound as x approaches a. As an example, we have this limit, the limit as x approaches 0 of the negative of 1 over x squared equals negative infinity. So that'd be an example of the kind of function that would do this. Okay, so this graph, it just plummets And so as x approaches a, this thing gets bigger, negative, bigger, negative, bigger, negative, bigger, negative, bigger, negative, from whichever side we want to come. Similar definitions can be given for one-sided limits. Okay, so we could talk about the limit as x approaches a from the left of f of x equaling infinity, or the limit as x approaches a from the left of f of x is equal negative infinity. Similarly, with x is approaching a from the right. And so all of these cases, we would say that f of x, the limit as x goes to a, either from the left or from the right, of f of x equals infinity or negative infinity, as the case may be. And we still say that those limits are infinite, even though f of x only goes to plus or minus infinity as x approaches a from one side. Now, remember what you've learned about vertical asymptotes. An asymptote is a line that a curve approaches. A vertical asymptote then is a vertical line that a curve approaches. So here's a definition. Vertical asymptote. The line x equals a is a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. And so the four pictures that we just saw, the curve can approach a vertical line on either side or both in the increasing without bound or decreasing without bound, either way. If that be the case, then the line x equals a, the vertical line, is a vertical asymptote. Example. Find the vertical asymptotes of the function f of x equals tan x. Now, we have this identity that tan x equals sine x over cos x. Okay? And so, well, the vertical asymptotes, they're going to happen when you've got a zero denominator, because you can't have a point there. So there are potential vertical asymptotes where cos x equals 0. In fact, since cos x approaches 0 from the right, as x approaches pi over 2 from the right, whereas sine x is positive when x is near pi over 2, we can say these things. Okay, so as x is approaching pi over 2, cos x is going to 0, and so we're zeroing out the tan function, and that's where we're going to have vertical asymptotes. The limit as x approaches pi over 2 from the left. Okay, we're going along that wave now, and x is approaching pi over 2 from the left. Now, the function is tan, which is not a wave. It's a periodic function with period pi. But it's going to blow up there, and as we approach pi over 2 from the right, it's going to plummet. So tan is going to have many cycles of this type. This shows that the line x equals pi over 2 is a vertical asymptote. Similar reasoning shows that the lines x equals any odd integer pi over 2, they are all vertical asymptotes of this tan function. So 1 pi over 2, that's a vertical asymptote. 3 pi over 2, 5 pi over 2, 7 pi over 2, negative 1 pi over 2, negative 3 pi over 2. We have all these vertical asymptotes for those values because those same x values, pi over 2, 3 pi over 2, all of those, cosine has a value of 0 for those. And in those cases, we would be dividing by 0, and so the tan function can't be defined and has vertical asymptote.